as very soon as an assistant professor.
Yes, yes. Thank you very much, Martin, for the introduction. Hi, everyone. Welcome to my talk today, Programming Support for Autonomizing Software. I'm Shiqing Ma from Purdue, and this is a joint work with my colleagues from Purdue University and one from IBM Research. So let me start this talk with one statement. Software can benefit a lot from being operated by AI. So what do I mean? So if you use AI to operate a normal program, you may have more benefits. For example, in Google data center, they use AI to replace the previously traditional simple heuristic-based solutions to control the temperature in the data center. And they will manage to save 40% by using this AI approach. However, traditional software are designed for human operators. So when they are first designed, they don't really consider AI operators. And this paper is trying to address this problem by providing a framework to support to train an AI model and deploy this AI model in production systems to let the AI operate the software. Many programs can benefit from AI operators. For example, parameterized programs whose result depend on the parameter configurations a lot, such as Canny program, which is an edge detection program. I show two images here. One is the airplane, and the other one is a trash can. We have two sets of parameters for these two images, and we get different results. For the first one, airplane, if you use the first set of parameter, you get very good results. You can see the shape of the airplane. However, for the second one, there are too many unnecessary lines. And for the second one, trash can, it's better to use the second set of parameters instead of the first one. There are many parameter tuning frameworks. However, they are still inefficient. And the second set of programs is interactive programs. These are programs which interact with human or the environment a lot, such as playing a game or testing the Android apps. Currently, there are some existing solutions, but they usually use random inputs or just based on some rules or heuristics. They are not very effective, such as testing the Android apps with the monkey tool. That's why we need autonomization to bring the intelligence to traditional software, to inject the AI to operate this software, and we can have the benefit of using the AI. There are already some existing works. However, mostly it depends on human. So humans have to define what to do. And this is very tedious and it's not portable, meaning that you have to do this for one app. And when the next app comes, you have to do it again. And it's a long process. You have to collect all the data traces, and you have to select the feature variables. You need to save them to the database, load them back when you need to train the model, and you need to feed them to the model to train and to do the inference. And then you need to integrate this model with traditional software. And to perform the training, you also need some other mechanisms, like the checkpoint mechanism. Like playing a game, when the Mario is dead, you have to restart the game again. And the other problem is the feature regression is very difficult. There are so many variables in the program. Which ones to use to train the model is very difficult. If you use the raw inputs, it's pretty, the inputs will be very hard because you need to pre-process these raw inputs to get to the internals and then to the final outputs. There are two traditional solutions. One is to use the raw inputs. As I said before, this is ineffective and inefficient. The other one is to ask humans to select the parameters to perform the training. These are mainly expert systems, but it requires a lot of human efforts. Our system, Autonomizer, is a programming framework trying to support doing this automatically. We provide a library having some primitives for the user to use in their programs to make the program automatically using AI to operate the software. These library calls are primitives that abstract the common tasks in autonomization, and it will allow users to use them in their original program. We also have the runtime support, which will translate the annotated program into a autonomized program transparently. And also to solve the feature expression per challenge, we also have a tool to analyze the program to automatically select the correct set of parameters for us to use as a candidates to perform the training and also inference during runtime. So here's the execution model of our framework. So first of all, we ask the users to annotate the program, replace some of the statements by using the library calls. The first line, AU extract X standards for the feature variables used as an input for the model. And during runtime, we'll collect all the concrete values of the X and store them into the database. AUNN, this is a neural network function. It will train the neural network and inference the values, output value Y, based on the input value X, using the model M with its own defined parameter and model structure. And our runtime will collect the runtime information and use a communication channel with a backend TensorFlow to perform the training and inference. And we'll store the data into the database as well. When we need to replace one variable in the program with the model prediction result, we use the function AU write back Y to replace this variable with our model prediction result. And we support two different types of training. The first one is random training, such as playing a game. If you just want to get the coins or get a high score, you can use random training, just like traditional reinforcement learning. Or you can do supervised training, such as for the Canny program, you can provide a set of data to say what kind of output you are expecting. And finally, the program is transparent to autonomize the program, and you can use it at runtime. So here is a list of our library calls, the primitives to autonomize the program. AU extract will annotate all the feature variables you want to use as an input to train the model. AUNN is a function communicate with the backend to train the model and use the model to make predictions. And finally, write back will update the target variable with the model prediction result and make the program forward, such as you can replace the keystrokes in a game with our model prediction result. To support the video games reinforcement learning, sometimes you need to restart the game. We also provide the checkpoint and restore primitives. These are used to restore a program state and then checkpoint the program state and then restore it later. Such as in games, when Mario is dead, you need to restart the game. You can do it with this. And the other problem we try to address is the feature variable selection. Our solution is a dynamic dependence analysis plus correlation analysis. For two different types, the reinforcement learning and supervised learning, we have two different strategies to solve this problem. We choose to use dynamic analysis mainly because we tried static analysis but end up with too many false positives, and the results were not very good. So for the supervised learning, the intuition to find the feature variable is to find the variable which are input dependent, and also it affects the target variables the most. So our analysis first perform the dynamic dependence analysis from the output to the input. Basically, we have a whole chain, and all the variables in this dependence chain will be the candidates because they are input dependent and also they will affect the output. And our intuition to select the best set is based on the intuition that it affects the output the most. So we actually rank all the candidate variables, and we select the ones which are close to the final output variable. And our distance is measured by the shortest path from the candidate variable to the final target output variable. So basically, on the dependence analysis, the dependence graph, we select the ones that are closest to the final output. But just to make sure, also we need to make sure that we select all the parents instead of just a single one. And for the reinforcement learning, all the candidates are basically the observable environment variables for the agent. And these variables will be continuously updated during the program execution, such as the position of the Mario, or such as the positions of the mushrooms in the Mario game. And in the second correlation stage, we try to remove many of the candidates by removing the duplicated candidates, which they actually have similar behaviors. For example, the pose X and row variable in the Torx, which is a car racing game. If we normalize two variables, if we normalize their values, they actually have the same behavior pattern, but before normalizing them, they actually looks kind of random. And because they essentially denote similar behaviors which can be learned by the neural network, actually we can just keep one of them. It's sufficient to train our model. We tested 9 programs, including 4 programs which are autonomized through supervised learning, and 5 are autonomized through reinforcement learning. And here I show 2 videos of 2 games, the Flippert and the Mario game. These are the videos played by our trained AI model. First, I show some of the program analysis results. First, I show the program names, the original code size measured by line of code. The third line is the added code by the developers using our library. As you can see, for many complicated programs, including Torx, we need less than 90 new lines of code, and most of them are trying to identify the feature variables, which we have a tool to help you to do that. And then the last 3 columns, we show the target variable, basically the variable we need to replace with the model prediction result, and the candidate variables we identified by our analysis, and the feature variables we selected after pruning. As you can see, the pruning process is quite effective. For example, for the candy program, it's for many target variables, we only need 1 final feature variable, but our candidates may be over 20. And this is the result for training time and the test scores. And we show the program names, and this is a baseline. For the games, we used 10 players, human players, to play the game and calculated the average score. And for the supervised learning, we actually use the default settings, different default parameter settings for their program. And the row value basically means we use the original input as the training data to train the model and perform the autonomization. And the middle basically means we randomly choose some of the variables in the dependency chain and then use them as the input to train the model. And the mean, basically, after using our pruning mechanism, we select the minimum set of variables used to train our model. This is just to verify the effectiveness of our feature extraction algorithm. And finally, we show the training time. As you can see, we only need half the time to train our model. And for many reinforcement learning tasks, if you use the other mechanisms, like using the original data or using some of the middle variables, it won't converge. And even though it converges in the breakout game, we only need half the time to train the model, which can behave competitively. Some of the static examples for one game, the Torx game, this is a car racing game, and training with raw input is very ineffective. I will show some of the numbers later. This is mainly because the raw images contain different car racing scenarios, such as the sunshine, the cloud, the walls, different road situations as well. And the existing work, which is an expert system trying to autonomize this program, it actually requires over 2,000 lines of code added to the program. As a comparison, our program requires less than 100 lines of code. And here is the driving score for the different programs. All basically is our approach, and the row basically use the original image screenshots as the training data to train the program. And menu, basically, we ask the developers to manually pick the internal variables and use them as the training data to train this model. And finally, the player is the we ask human users to play this game, and we use this as a threshold, as as an expert to measure how our system performs. As you can see, if essentially the expert system and our framework can achieve similar performance with human players. However, we require less lines of code. Even though the expert system is surely faster, they require 14 hours of training and require 20 hours of training. But if you use raw images, the driving score is very low. As a conclusion, we proposed a novel technique to support the autonomization of existing software, which usually require a lot of interaction with the environment or human, which was tedious if you don't have the programming support. And we provided the library interfaces and also runtime support to automatically autonomize those programs. And we also provide tools for the most tedious part, feature extraction. We evaluated our framework on 9 real-world programs for supervised learning and also reinforcement learning. The results show that we need less training time or we have higher model quality compared with existing approaches. And our work is open source on GitHub. You can download it and have a try. Thank you, and I'd like to take questions.
Any questions? If not, I have one. Actually, so I'm Martin Maas, I'm from the Google Brain team. I should have said that at the beginning. It looks like your approach is looking at variables within the program.
Yes.
And the baseline is at the very other end of the spectrum, where you look at the raw inputs, more like what an agent in a real environment would see.
Right.
So is there an intermediate point where you, for example, look at, say, for example, the content of the memory, but not knowing what the variables are?
Oh, yes. Thank you very much for the question. Actually, this completes my talk. We do have some results here. As you can see, for the 2 reinforcement learning programs, we don't show the numbers for the candidate variables or stuff like that. This is because we also support binary. So basically, you can give us a binary and we can analyze the memory addresses and their variables and collect their traces, perform the analysis, and find the places we can instrument. We also have a well-grained version of autonomizing the programs. So these, as shown as these 2 games are actually autonomized by using well-grained and KVM. Thank you.
Let's thank the speaker again.
Thank you.